Hello, everyone. And today I'm going to talk about our TrajNet++ benchmark, which has been a part of the long-term human motion prediction workshop since last 1 year as well. So the TrajNet challenge was a part of the third workshop as well. And today what I'm going to talk about is about an update, like what have been the updates on the TrajNet++ challenge over the last 1 year. So those who are unfamiliar with the TrajNet++ benchmark, so it's basically a benchmark for objectively evaluating trajectory forecasting models. And why is this benchmark different? Well, because in this benchmark, we are more focused on interaction-centric scenarios. Like we do the task of trajectory forecasting, but evaluate them on scenarios where the agents are actually interacting. Because there are many cases in dataset where an agent is either moving linearly or static, and evaluating on such agent is not so meaningful. So in this benchmark, we actually sample scenarios where interactions take place. And we focus not only on the distance-based metrics like average displacement error and final displacement error, but also socially aware metrics like is there any collision taking place or not. So the TrajNet Plus, and with regard to this benchmark, we have released the TrajNet++ challenge that is hosted on AI Crowd. And since its inception, there have been more than 300 participations and more than 1,800 submissions on the TrajNet benchmark. And for someone to get started with using TrajNet++ benchmark and some trajectory forecasting baselines, we had also provided resources on our GitHub repo called TrajNet++ baselines. So this year, like last year, the TrajNet++ challenge was a part of the ICRA workshop, but then we had a surprising result, is that there have been no new winners, no new leaderboard winners since the last year's challenge. And so I would like to take this opportunity this year that based on this observation to answer two questions. As TrajNet++ is more about a meaningful evaluation, let's take a look at what the current research is actually evaluating on. So most of the recent papers, I have cited some of the recent papers, it's a non-exhaustive list, currently show that their method is superior on other methods using only the top 20 average displacement error and final displacement error metric. Basically, they tell their model to output 20 samples, and then they take the sample that is closest to the ground truth. And as a running example, here I have shown two models whose code is open sourced and fairly well known, and who are using the same data split. So you can see that they are pretty close to each other when they are evaluated on top 20 ADFD. But the issue here is that this performance can be misleading when you only consider this single metric. And why do I say this? Well, to prove my argument, I take a simple uniform predictor, as you can see on the top right, where given the current, at the end of the observation, given the current position and the velocity of a pedestrian, I give 20 uniformly spread out predictions given based on 4 velocity profiles. As you can see, the 4 arrows per direction and 5 different directions. Now taking the open source repo of STGAT and just replacing the model with this simple uniform predictor, we get a very surprising result that the results are very comparable to each other. There is not a lot of huge difference. So evaluating using only the top 20 ADFDE might not be the most objective evaluation out there, which are being used by the most of the methods right now. Another point I wanted to talk about is the collision rate. Now, collision rate is a very important indicator of a social acceptability, the social acceptability of outputs provided by the model. And you can see that the collision rates vary significantly across different methods. And it is very important to consider this metric as well. So there are 3 high-level issues with the current evaluation, where evaluating only on the top 20 metrics is not the best way to move forward. The collision rates are missing and they should be taken into account. And also reproducibility is kind of a challenge because different methods use different pre-processing techniques. So it's not an objective evaluation, and sometimes there are issues with reproducing the numbers with the officially released training scripts as well. So this is where we feel that TrajNet++ is highly important as an evaluation benchmark, because one, we focus on the top 3 ADE-FDE, which is a more stricter metric, and it filters out the uniform prediction issue I mentioned a few slides ago up to an extent. It also focuses on the collision metrics, and reproducibility is no longer a huge issue because we have a fixed training and testing set. And also from our side, we open source our baselines so that each and every number is reproducible. So this is the first question we wanted to tackle. And the second question is, given that there are no new winners, we wanted to look into detail that why do recent submissions were not able to top the leaderboard. And what we realized that the top 3 methods, which I have shown here on currently the AI Crowd leaderboard, they are actually utilizing the training strategies which we have proposed in the TrajNet++ baselines. And this is something I wanted to talk about, that what are these training strategies that can help your forecasting model to give less outputs that undergo less collisions. So here I will talk about what we feel is the training recipe for training socially aware forecasting models. And if you want to develop your models, you can make use of this recipe and build upon it further. One is the different training paradigm that we use. Second is the importance of having spatio-temporal interaction modeling. And third, we also realize that the loss functions can play a huge role while training these models. So the first is the training paradigm. A majority portion of the current work actually undertakes a training paradigm where they predict the future trajectories of all the agents in the scene. Like given the past trajectories of the 5 agents I've shown here, it will simultaneously predict the trajectories of all the 5 agents. And the problem here is that many of the agents are static or move linearly, and they can hamper the process of learning social interactions. What we propose as a training paradigm is that TrajNet++ explicitly categorizes samples where the primary agent that we show in red is undergoing social interactions. So during training, we propose that let us use the ground truth of the neighbors, that the neighbors will follow what they did in the reality during the training stage and only predict the future of the primary agent. And since we use an intelligent sampling in TrajNet++ that the primary agent always undergoes interactions, the model is forced to learn the underlying social interactions. And here, I would like to clarify that during test time, we predict all the agents simultaneously. It's only that during training, we focus on only learning the future of the primary agent. So is there a difference because of this training paradigm? Well, there is a significant difference, as you can see here, that given the TrajNet dataset, if we predict all the agents during training, it has a significantly higher collision as well as average displacement error and final displacement error as compared to predicting only the primary pedestrian during training. And note, during test time, we predict all the agents at once. And in all these experiments that I will show, we utilize the directional grid module that we proposed in the TrajNet++ journal paper. So this is one point where we feel that current methods are not able to overcome the leaderboard. The second point is spatio-temporal interaction modeling. We propose to do interaction modeling at every time step. Many of the recent methods stop doing interaction modeling at the end of the observation period, or they perform interaction modeling only once, for example, in social GAN, just after the end of observation period, in the hope that it will save some time computational resources and the inference time is faster. But because of not doing interaction modeling at each and every time step, these models suffer in learning the concept of collision avoidance. So if you perform interaction modeling only till the end of the observation, all other factors kept constant, you can see that the average displacement error and final displacement error are competitive, but the collisions are almost 2.5 times higher as compared to performing interaction modeling at every time step. So we believe that while developing new trajectory forecasting models, one needs to perform interaction modeling at every time step. And finally, the loss functions also end up playing a huge role in terms of the accuracy of the models, in terms of the distance-based metrics. So one of the common loss functions that is used is the L2 loss, which is L2 error between the predicted positions and the final positions. On the other hand, we see that there is a huge benefit of using a Gaussian loss. The only difference being that along with predicting the XY coordinates of the future velocities, we also predict the variance at each time step, the uncertainty at each time step. And because of this learned variance, there can be less penalty on tougher uncertain samples. In other words, if a sample is too difficult for the model, and if it is penalized the same way as a simple sample, then the gradient can be really high and can change the training process of the model. While if we have a learned variance, there can be a lesser penalty on such tougher uncertain samples, and the training process is much smoother. And this has also been discussed in literature, and it can be interpreted as a learned loss attenuation, that where the model is not so certain, it is not penalized a lot. And because of this difference in loss objective, we see that there is a huge impact on the accuracy of these models, especially in interaction-centric scenarios. So as you can see here that when I train with L2 loss, the error is too high as compared with training with the Gaussian loss, while the collision metrics are still close to each other because we are doing spatio-temporal interaction modeling and following the same training paradigm. And if you use auxiliary loss functions like having a collision loss when the primary agent collides with the neighbors, you can further reduce collision metrics. So auxiliary loss functions are other tricks to further reduce the penalty on the collision metrics. And so we believe that this training recipe is very important to have a lower ADFT as well as a lower collision rate. And our TrajNet++ baselines, on which the top 3 models in the leaderboard have been built on, already have these attributes. It uses primary pedestrian-based training. It uses the Gaussian loss function. Moreover, it handles the partial trajectories. There are many cases where a model is not able to handle cases where a neighbor is present in the scene only for a small amount of time and not the entire scene duration. Our repository can handle that. And more importantly, we provide training scripts that can reproduce all the numbers that I showed in this presentation. So please to have a look. And finally, something that is a work in progress towards our goal of open science and reproducible methods. We are launching this TrajNet++ model zoo, where we not only provide training scripts of the experiments we perform, but we also take external repositories which are out there and evaluate them on TrajNet++ and also provide the training scripts for the same. We highly encourage the researchers to add their training scripts and submissions to our TrajNet++ model zoo, and the link for the same is given here. In conclusion, we highly believe that the TrajNet++ benchmark is a need of the hour for efficiently evaluating trajectory forecasting models. It provides a meaningful objective evaluation. Our TrajNet++ baselines repo with its training recipe for training socially aware models can help you kickstart developing your forecasting models. And finally, in efforts for open science and reproducibility, please do consider submitting your works that you develop to our TrajNet++ model soon. Thank you everyone for your attention. If anyone has any questions.
Any questions from Zoom or the crowd? No questions? On Zoom also, no question? Awesome. If not, we can switch to Andre.
Yes.
Thank you, Parth.
Thank you.